the consideration of the paradox or analogous paradoxes had a very momentous impact on the development of contemporary mathematics. Could you quickly reconstruct this history, how mathematics changed and what they were trying to do, and what's the role of the paradox in that?
Okay. So this brings us to the other class of paradox of self-reference, which we talked about briefly earlier, which are the paradox of set theory. Let me give you the simplest and most famous, and then we'll talk about the effects of this. Okay. So this was a paradox that was discovered by Bertrand Russell, usually called Russell's paradox. And it doesn't use the notion of truth, it uses the notion of sethood. So you can talk about sets of things, you know? The sets of people in this discussion, that's just the set containing you and me. The set of people with coronavirus, well, that is slightly larger at the moment. Well, I mean, has larger in size, in number, shall we say. So you can talk about collections of things. Okay. Collections of red things, collections of capital cities of the world, collections of blah, blah, blah. All right. Now, some collections don't seem to be members of the very collection. So consider the collection of all capital cities in the world, right? That's obviously not a capital city. It's not obviously not a city, right? So the collection of all capital cities in the world is not a city, so it's not a member of the collection of all capital cities in the world. On the other hand, it does seem to be the case that some sets are members of themselves. So, for example, the set of all abstract objects. Well, that's kind of an abstract object, so it's a member itself. The set of all sets, hey, that's a set, yeah? So obviously it's a member itself. So it seems to be the case that some sets are members themselves and some are not. Okay, so take this slowly. Let's consider the set of all those sets which are not members of themselves. So that's going to include the set of all capital cities, but not the set of all sets. Okay, let's call this the Russell set. So the Russell set is the set of all those sets which are not members themselves. We're going to ask a question and you can guess what it's going to be, right? Is the Russell set a member of itself? Is the Russell set one of these sets that's not a member of itself? Well, hey, geez, if it's a member of itself, then it's one of these sets that's not a member of itself. Oh, so if it is, it isn't. But if it isn't, well, it's a set that's not a member of itself, so it is. Okay, you can see the similarity with the liar paradox, right? We're using the notion of sethood, not the notion of truth, but you can see that in some sense, which is kind of hard to articulate in detail, the similar sort of things are going on.
Would you say that what there is in common is that we are in front of a proposition which entails its negation? Is that what all these paradoxes have in common?
No, because that feature is common to the liar and to the Russell paradox, but there are paradoxes in the same family which don't have this feature, like the Berry paradox and Koenig's paradox. I mean, we can talk about those, but let's stick to your question for the moment. Well, what seems to be going on in both of these is that, in some sense, you're talking about a self. You know, the liar talks about itself. The set of all sets that aren't members themselves seems to be applying to itself. Okay, I mean, that's the kind of obvious intuitive thought. Cashing that out is hard. Anyway, Russell discovered his paradox right at the start of the 20th century and sent it to Frege, who was devastated. Now, why was this so devastating? Well, now we can come to your question. The 19th century in mathematics was the century of mathematical rigor. So, of course, mathematics had been going on for a long time before the 19th century. But a lot of the ideas were a bit slippery. People didn't know how these things worked properly. In particular, by the end of the 19th century, mathematicians knew that there was an enormous menagerie of kinds of numbers. There are natural numbers, 0, 1, 2, 3, 4, 5, 6, okay? There are negative numbers, the negatives of those. There are fractions like a half, a third. There are irrational numbers like pi and e. By that time, they knew there were infinite numbers like Aleph naught and 2 to the Aleph naught. There are infinitesimal numbers, numbers which are so small that they're not zero, but they're smaller than any rational number you can think of. And so there's this enormous menagerie of things. And they weren't particularly well understood. They seem to give you contradictions quite easily, like the infinitesimals. But what happens in the 19th century is that mathematicians make enormous progress in setting these things on a firm and a well understood foundation. This was a lot of this was done by sort of German mathematicians, but there are a few French ones. So that by the end of the 19th century, people had a pretty good understanding of complex numbers, rational numbers, irrational numbers. Infinitesimals had gone out the window. But all the other kinds of numbers turned out to be things which you can construct from the natural numbers, 0, 1, 2, 3, 4, and so on, by simple set theoretic combinations. So that left the big question. Okay, what are the natural numbers? How do you understand those? If we can understand those, and the ways that you can manipulate those set theoretically, then this sort of morass in the foundations of mathematics would have been worked out. And that's essentially the problem that was driving Frege. Frege wanted to give an account of the natural numbers, and he wanted to show that not only could you define these in terms of sets, but you didn't need anything other than sets to define them, so you could have reduced the whole schmozzle to set theory. Not only that, but set theory, Frege argued, was a branch of logic. So the basic principles of set theory are just principles of pure logic. Things like X is a member of the set of red things if and only if X is red, etc., etc., etc. Well, that sounds pretty logical, okay? So Frege's actual definition doesn't sound initially too promising, but he says something like this. Well, what's one? One is the set of all those sets which have just one thing in. And two is the set of all those sets which have just two things. So that sounds pretty circular, right? But in fact, you can get around the circularity. So Frege had a definition of natural numbers, and therewith all the other kinds of numbers in terms of pure sets and in terms of pure logic.
Could you tell us briefly how you might hope to get a theory of all the other numbers just by having a proper account of the natural numbers? Why natural numbers? Why are they foundational in that sense?
Right. Okay. So you can define all the other kinds of numbers in terms of natural numbers. Let's not hammer through all the details,
No,
but let's just do a couple. So take rational numbers like a half. You can define a rational number. I mean, half is a kind of pair. It comprises 1 and 2. Okay, so the first cut you might want to say, well, it's just a pair of numbers subject to various manipulations which you can define on them. That ain't quite right, because a half is the same as 2 fourths, and 1 and 2 is not the same as 2 and 4. However, you can fiddle a bit. Okay, 1 and 2 and 2 and 4 obviously related by a very simple, in a very simple way. One is, you get 1 by doubling each of the other. And so if you fiddle around with this, you can take a rational number to be not a pair, but what mathematicians call an equivalence class of pairs. So it's 1 and 2 and things like that. Okay. So that's how you do rational numbers. Irrational numbers like pi and so on are a bit trickier. And there are several constructions you can use, but one of the most famous was discovered by the German mathematician Dedekind. So suppose you line all the rational numbers up in order of magnitude. So you start with 0, and then you get quarter, then a half, then let's just consider the ones between 0 and 1 to keep things simple. 0, a quarter, a third, a half, 2/3, split up 1. Okay, so you've got this infinite array, and what you do, says Dedekind, is you schnit, you cut in the middle, right? Choose anywhere and you cut, and some cuts are going to have the biggest number. So if you cut at a half, okay, you put the half in one cut, all the other junk in the other stuff. When you cut at a half, all the things less than or equal to half are going to have the biggest number, half, but the things greater than won't. But, and here's the clever thing, sometimes you can cut where there's no rational number to divide. So if you take, for example, some irrational number between 0 and 1, such as, I don't know, a quarter of pi, then every rational number is going to be either less than that or greater than that. But when the class of things that are less than that is not going to have a greatest number, and the class of things that are less than that are going to have no greatest number. The class of things that are bigger than that are going to have no greatest number. However, what you can do is you can identify that irrational number with one of those bits, or with both bits if you like to put them together. So you can identify an irrational number with a cut in the rational numbers, and that's the Dedekind construction. That's the most standard one that you find in mathematics nowadays. I think that'll probably do as a way of explaining how you can reduce some of these other numbers.
Yeah. So let's go back to Frege's dream and.
Yeah. So Frege had this definition of the natural numbers in terms of sets and nothing but sets. And he was using principles of set construction, such as, well, something is in the set of P's if and only if it's P. Something is in the set of red things if and only if it's red. Something is in the set of numbers. Something is in the set of real numbers if it's a real number. Something is in the set of sets if and only it's a set. And it was fiddling around with that principle that Russell realized that you've got Russell's paradox. So there's this principle of naive set theory, which says something is in the set of so-and-sos if and only if it's so-and-so. Something is in the set of red things if and only if it's red. And that's a bit like the T-schema. Okay, it's this general principle. And if you apply this general principle, you get Russell's paradox. So Frege was devastated. He thought his life's work was in ruins. And he published not a great deal after that, in fact. I mean, what he'd done in the process of all this was found modern logic, but that wasn't recognized as his great success until sometime later. So, I mean, Frege is probably the most significant logician since Aristotle, but not for the reason that he thought. So Russell was, in the philosophy of mathematics, Russell was also inclined to Frege's programs called logicism, seeing mathematics and ultimately set theory as a branch of logic. And he tried to pursue this program in his own way. He published an influential book in 1910 with his ex-mentor, Alfred Whitehead, called Principia Mathematica, where he tried to sort of solve Russell's paradox and give his own version of logicism. That didn't really work either. I mean, didn't really persuade many people for very long. So nowadays,
type theory, right?
There's type theory, and it's a bit like Tasker's hierarchy of languages, and it's problematic for very similar reasons. So, in mathematics nowadays, there is a sort of orthodox solution, but this wasn't Russell's. It was sort of specified by another German mathematician, Ernst Zermelo, and his work goes back to about 1905. And what Zermelo says essentially is this: take this principle, the naive abstraction scheme. Something is in the set of so-and-sos if and only if it's so-and-so. It's instead of red things if and only it's red, and so on. You can't have it. You've got to get rid of it. Okay, well, that's the easy bit. Trouble is, we seem to use it quite a lot. So the trick is to have just enough of it to get what you want in mathematics and no more. And Zermelo suggested what that would be. He didn't quite get enough in the first cut, so Zermelo's axioms were extended later on by other people. But essentially, Zermelo's approach has triumphed. You can get enough of this comprehension principle to do most of the things you want in mathematics. You can't have everything, but you can get most things. And something like that is the orthodox way that set theory is now treated. The set theory that emerges from this looks nothing like logic. Okay? These look like far too contingent propositions about the nature of sets. So no one nowadays thinks that set theory is part of logic. Or at least not many people do. So the logicism program of Frege and Russell failed, but set theorism has fared very, very well in the last 100 years. So you can do most of the things really everything that standard mathematics wants to do with sets using Zermelo's axiomatization. It's turned out more recently that you can't sort of do everything you want. Zermelo's axiomatization did everything that mathematicians wanted to do circa 1905, maybe circa 1940, but we now know that there are bits of mathematics which don't really fit very well into Zermelo's axiomatization. One of these is category theory, which is a much more modern branch of mathematics, which really does not fit very happily into set theory. So, I mean, Zermelo's axiomatization certainly does have problems with the more modern parts of mathematics, but for the sort of part of mathematics in the first half of the 20th century, it does a pretty good job. So the responses to Russell's paradox drove a lot of discussions in the foundations of mathematics and later on in set theory for a very long time, probably continued to do so in many ways.